Okay, welcome everybody. Today is a special day. We are going to have our 8th lecture of the series, which is the first lecture of quantum mechanics. The reason why it's special is because we already had this lecture more than a month ago. And what happened is that I didn't hit record on the Zoom screen. So we don't have any good audio, and you only have a video of an hour and a half of me writing down things on an iPad. That is useful to nobody. So because of that, I decided to re-record this lecture. That's why you see me, I'm in a different room. And we're going to basically go through the same discussions and the same concepts that we had. But I have kindly asked two people, two undergrad students, awesome undergrad students that are working with me and Cal, to join me today, because I will not be able to transmit the same energy if I was talking to an empty room. You two, would you like to introduce yourself to the future audiences?
Yep. Hi, my name is An. I'm an upcoming senior, and very nice to be in the class.
Lauren, what about you?
Yeah, hi, I'm Lauren. I attended a few classes, I think more or less the entire summer last year, and I'm also excited to attend again this year for a few classes.
Excellent. So thank you. Our time budget is around an hour and a half, but probably less, because I think I will be able to streamline a bit more the activities that we're going to do. Ask questions as you would in a normal class. I hope that this is useful for you. And if you already know all of these things, well, I'm very glad that you joined me to make the lecture easier. So before we start, a couple of reminders. Remember to be nice to each other and to yourselves. The second part sometimes is harder than the first, but I trust you are able to make it. This is a usual slide where we have the resources for anybody that is joining us for the first time. This is where we have all the lecture materials, the forum that we use to communicate, the YouTube channel that you're probably watching this there, and the GitHub repository where we have many of the online guides. So for today, this is a menu of what we're going to discuss. I want to spend a big chunk of time giving you thoughts about quantum mechanics and what does it mean to model nature in general. These are my own thoughts, shared by many people. You don't have to share them, but I want to share them with you. You don't have to resonate with them, but I want to share them with you so that you have this perspective. We're going to talk about Dirac notation, we're going to talk about the Schrodinger equation, and we're going to solve one problem. For the original lecture, I meant to solve two, and I realized that there was nonsense. We didn't have enough time, so we're going to focus on one specific problem. So let me stop sharing here. So this is what we're going to discuss today, the thoughts on quantum mechanics, on model and intuitions. We're going to talk about ants and water. Thank you. We're going to talk about representations, skets, Dirac notation, the Hilbert space, and Schrodinger equation. I'm going to give you a couple of examples of the Schrodinger equation. And then we're going to play with a magic box that I brought for us to have an activity. And then you're going to make some calculations with the infinite square one. Thing is recording well? So these are my pictures and my thoughts, things that I'm going to share with you. But the first thing that I want to talk about, more than quantum mechanics, I want to ask you in general, what does it mean to model nature? Model, and I'm going to put in here a word, understand, maybe, explain. What is in your head whenever we talk about, I'm going to present you, for example, the BI model for specific heat of solids. I don't know if you have seen that. Maybe you have seen that in your condensed matter classes. But whenever somebody comes and tells you about a specific model to understand something, what is in your head that you want to share?
For me, it's like my immediate thought. I just
Please.
There'll be some equations that describe some physical properties of an object, and that equation can be applied to a lot of objects. That's how I think about model nature.
What about you, Lauren? What comes to mind? There is no right or wrong answer.
It's not trying to explain every single thing, and usually is trying to, at least in first steps, just getting the big picture and what like we are characteristically describing limited things, but so we can model not just what we see, but also make predictions.
I like that word. I like the word limited. That's kind of at the heart of the things that I want to transmit to you. What comes to my mind when I think about these things is very similar to many of the things that you have described. Is we have something in nature, a behavior, an object, a phenomena that we would like to understand better, to be able to explain in terms of maybe smaller objects or in terms of more fundamental laws. Why is this happening the way that it's happening? Yet I share a view that not every scientist that you will talk to will share the same view. And I feel very strongly about this, that we will never be able to fully understand nature in its entire complexity. And there is many reasons for that, but in particular, if you needed a computer to model exactly what is happening in the universe, probably the computer should have the size of the universe or more. So we'll never be able to actually get to fully understand all the mysteries that nature has for us. Instead of seeking that, I think what makes sense is to try to write down equations, write down models, write down ideas that describe some parts of nature in terms of other parts. So you will choose your degrees of freedom. For example, if you're trying to describe, I don't know, what happens to a bunch of billiard balls as you're playing billiard in a pool table, you're going to use classical mechanics. You're going to treat each ball as in its own body that maybe doesn't deform, etc., etc. If you're trying to describe how planets orbit around the sun, you're going to treat each planet as its own thing. You're not going to worry about how many billiard balls are in each one of the planets and so forth. So there are certain things that you are able to explain. And whenever you write a model, this is another important word that I want to put, break. There is going to be limits. That is a word that I like from what you said. After which, if you push your model further than those limits, it's going to start breaking down. There is going to be behavior that you're not able to explain. Does that make sense? Having this picture, I think, helps a lot because it frees you from having to have too many deeply unsettling philosophical questions like, but does nature really work that way? Well, no. Nature works in the way that it works. We're never going to understand that. We're trying to explain some aspects of that. The reason why I say that is because whenever we talk about quantum mechanics, and especially in the first time that you're being introduced to the subject, the language, the mathematical language that we use to describe it is going to sound very weird. And you're going to feel like, wait a minute, that makes no sense. What do you mean that now we have to talk in terms of wave functions? What do you mean that the electron is everywhere at the same time, but whenever we measure somewhere, it collapses the wave function there? What do you mean that things are probabilistic and that I cannot have a coherent description of what happens in nature without having to invoke this randomness? And when I was sitting in your chair at your age and stage, I remember taking my first classes of quantum mechanics and thinking, yeah, the adults got all this wrong. They're idiots. They don't know what they're doing. Whenever I grow up, I'm going to be able to prove that this is an incorrect way of describing these things. And I felt the same way as many other people that have that strong, reactive, defensive feelings against quantum mechanics in the beginning. But if instead of saying, I'm going to learn how nature truly works, you throw that out of the board and you say, I'm going to try to learn this framework that explains many phenomena in nature very well, that's another story. And you can feel a bit more comfortable. Before we dive into that, just in case there's some lingering thoughts of uncomfortability on your side, I want to give you the following example. I want you to think in terms of sizes. This is you two, Anna Lauren, sitting there and listening to me monologue. Your typical size is order 10 to the 0 meters. You may be a meter and a half, a meter 0.7, a meter 0.3, a meter if you're very short, but order of magnitude, your size a meter. That are human characteristics sizes. If you think of an ant, I'm going to make the best ant that I can. An ant is 10 to the minus 2 meters. A typical size for an ant is a centimeter. That is a drop of 2 orders of magnitude only. You still can see an ant with your eyes. And I have these pictures. These 2 beautiful pictures of ants playing with water. Now, the reason why I want to show you this is because as soon as you go and you drop 2 orders of magnitude in the sizes of the universe, water stops working the way that you're used to. Immediately, things change a lot. That has to do with a competition between surface tension and gravity. Surface tension is a much more important force at these scales than it is at the scales that we have. So if I were to drop you at the size of this ant, and you were sitting here with it, you will be bewildered and so confused that water works this way. You're like, wow, and I can hold a tiny drop of water in my ant-sized hand, and you will have a blast until something happens, and if you are not careful on how to treat that water, you may die. This is a picture of an ant that died because it got trapped in the water. For us, water doesn't behave that way, so you don't have this intuition of how you need to be careful about that. Does that make sense? That was a 2 order of magnitude drop. An atom, and we'll see that in the quantum mechanics classes that we already have had, because we already have solved the Schrodinger equation for an atom. The hydrogen atom is 10 to the minus 10 meters in size. The nucleus is 10 to the minus 15 meters. 10 orders of magnitudes drop to go to the size of an atom, and 15 orders of magnitude drop to go to a nucleus. Nothing has to work. Nothing has to have any resemblance to any intuition that you have had. Just the fact that we're able to write any math that is able to make us be able to make any numbers that make sense for reality is already a miracle. So whenever we are going through these concepts and you start feeling uneasy, that goes for both of you and for everybody that is watching us in the future. This uneasy feeling like, what does it mean that the particle doesn't have to behave like a baseball? That is the type of things that you're used to. Does that make sense? Any questions so far before we actually start talking about quantum mechanics and the Schrodinger equation?
There's like a thing like, I don't know if it's joke or not, I've never experimented with myself, but it's like if you drop an ant from like a very tall building, it wouldn't die.
For example.
Because the wind and all the
For example.
air resistance.
You see? And it's 2 orders of magnitude. That's another very good example. And little heights have a different meaning in the ant world as it does in our world. So be grateful that at least some of the things that we're still thinking make sense. Okay, thank you. Any other comments on questions?
Pablo, if I think it's quite easy for us to get a physical intuition for the classical world. Not just from the equations, but because it's much more easier for us to imagine such things since we see them on a daily basis. How do you end up building an intuition that's as fluent as for classical, but for quantum, when you are not always every day seeing such phenomena?
That's a very good question. A big part of that is you have to abandon tying it to anything that you have seen in general. It's kind of similar to when you're reading a very good story, a fantasy story, and the author writes in such a way that you get immersed into this world, and suddenly you're not questioning the fact that the main character is able to do magic and conjure a dragon out of thin air. You actually, if you have been following this main character for the whole saga, you're expecting them to do that. So it comes with time. It doesn't come immediately as you start reading the book that you feel comfortable with the fact that there's zombie dragons flying around. The best way that I can think of is by trying to get comfortable with the math, letting the math guide your intuition, and then honing the intuition to guide the math, and having those two feed into this cycle that from time to time you feed into it experimental observations. For example, that's one of the things, this is a perfect segue, because what I was going to describe is the type of experiments that made us start realizing something is off. Something, the way that we're describing things in terms of the Lagrangian mechanics or Hamiltonian mechanics, classical mechanics, is not working in these realms, in these orders of magnitude. So whenever you have these experiments, and we're going to talk about one of them, actually I was going to mention it, is one of the most famous experiments, the double slit experiment. I'm going to describe it in a second, but as you start realizing your intuition doesn't work very well, thanks to the sweat and tears of a lot of people, we have a mathematical model to describe what is happening. You start imagining things like, oh yeah, what if you imagine that the electron is this kind of wave that is moving in some way, and then suddenly, for example, the way that I imagine it is the electron is propagating as a wave, but whenever it interacts with a detector, this shock of electricity, which I'm imagining is an electricity, but of course it's not electricity, sends it through the entire wave, and it collapses into a single point to interact with the detector. That's how I imagine it. And thinking in terms of that wave, for me, the wave makes this interfering pattern that we're going to talk about in a second. But that came from thinking about the math and the experiments and trying to put all that together. And through years of thinking about it and trying to come up with different ways of explaining the experimental data that we see. That's the best that I can tell you. Yeah, that is the best that I can tell you. Of course. But thank you for the question. It's a very good question. So the situation that we had at the beginning of the 1900s was a lot of physicists were very arrogant around that time, a little bit before, and they felt that we have basically explained everything that there is to be explained in nature, and future generations of physicists and scientists will only have to content themselves with calculating constants to bigger decimal values. So like, oh, the gravitational constant G. The future physicists are just going to be trying to get more decimals out of obtaining this constant. And a bunch of things exploded at the same time. Things that we didn't know how to explain. One of them is called the ultraviolet catastrophe, which is if you try to calculate the black body radiation emitted by a box, you end up obtaining infinity. The details don't matter, but part of the problem was if you were to think that the energy spectrum of the photons is a continuum instead of a quantized spectrum, you end up obtaining something that blows up. There were questions about the speed of light, and it seems that however we measure the speed of light, independent on how the Earth is rotating at that moment, seems to be the same number. But that makes no sense, because if light is propagating at the time we thought in a medium, depending on if you measure the speed of light when the Earth is traveling in one direction with the medium with respect to another, you should obtain a different value. That is what led to special relativity. And many other things that led to, for example, the emergence of complexity and chaos theory, that basically tells you no matter how well you understand the rules of the game, in nature, you're never going to be able to fully explain what is happening. So one of the experiments was thinking if you have a bunch of particles that you're shooting off, these are particles. So I want you to imagine them as marbles, as these billiard balls that we were talking. In this case, these can be electrons. So you shoot a bunch of electrons and you have a wall with two holes. The holes have to be small enough to make sense for electron to interact with the hole. If the hole is this size, it makes no sense. It will not make any of these interesting phenomena. But if you were to shoot these electrons, these marbles, and they are truly marbles, what you expect to obtain on the other side is a distribution of counts that maybe follows some pattern like this. Perhaps it's a bit more here and then a bit more here, and that's it. But it's kind of a continuous pattern. After you shoot 100,000 electrons, you make a histogram and you will obtain something like this, in where there is a peak here, there is a peak here, because it's easier for one of the electrons to hit that, it's easier to hit that, and then an electron that bounces here and here, maybe it's less likely. Does this make sense? Turns out that the pattern that you obtain doesn't look like that. The pattern shows a very characteristic, what is called interference pattern. Let me try my best to make it happen. In where you have regions of minima and maxima. I try my best. You have regions in where no electrons seem to appear here, in these 4 places that I'm putting, and a bunch of electrons seem to appear in these places that I'm putting. And that is a pattern that we have observed with waves. If instead of doing this with electrons, you were doing this with water waves, I don't know if you have seen this experiment or play with this in a pool, the wave basically passed through both holes and they start interfering with each other, and they form this pattern on the wall in where there are locations in where the wave cancel, the water doesn't move, there are locations in where the wave enhance each other, and then the water moves a lot. So we're like, that makes no sense, because the electrons are supposed to be a particle. So, well, maybe not, they're not, maybe they are a wave. That doesn't work either, because we can make the experiment in such a way that we shoot only one electron at a time, and every time that the electron passes, we hit a ping, ping, ping. The electron starts appearing as dots individually every time that you shoot one. So they really are moving as marbles. They're hitting the detector as a marble would. It's just that when you make many, the pattern appears in where they were places that they were not going to for whatever reason. So this is called the double slit experiment. And it's one of the many experiments that show there is something weird happening with very small particles in terms of our classical descriptions of them. Any questions so far? Does this make sense?
If I were to put like a detector at the two holes, and I guess if you shoot the particle one by one, you get the kind of the classical behavior of the electron.
Yep. If you put a detector here and here, so that the detector, one of the detectors fires and tells you the particle passed through here, the interference pattern disappears. And you end up obtaining the two blobs that I was talking about. It's even crazier, depending on how sensitive your detector is. If your detector is very sensitive, so that you are very sure that the particle passed through this hole, the interference pattern disappears completely. If the detector is not that intrusive, it just gives you a signal, most likely the particle passed through here, the interference pattern is kind of blurry, but it's still there, which is very weird. It's almost as if nature didn't want you to see from which hole this particle actually passed.
And what is the kind of like the size of the hole that you have to shoot through?
I don't remember, but it has to be commensurable with what we call the wavelength of the electron. It has to be tiny.
It has to be tiny.
It has to be tiny. Yep.
And there's like is there any like intuitive reason for that? I don't know. It feels to me like what's the difference when you have like I see.
Wait, what?
I don't know. I was kind of imagining when the hole is kind of like the electrons, you can't have some of like that's when the wave property of the electron kind of like come into play. I feel like, but there's no, I don't have a good intuition for it.
It's difficult to come up with an intuition for it. There is a lot of philosophical discussions of what quantum mechanics means, because the way that most textbooks will tell you is if you make a measurement of the electron's wave function in one of the holes, that collapses the wave function. We'll talk about that in a second. That collapses the wave function and makes it in such a way that then it propagates as a particle. But the concept of measurement is intrinsically human. That seems to be a human thing. So you're telling me that a human has to be present and has to acquire knowledge, and whenever you acquire knowledge as a human, that messes up with how the electron is propagated. That's so weird. And there is an entire branch of quantum mechanics that they really think that is intrinsically related to consciousness. I don't want to talk about that in this video, in this lecture, because I have no idea how to interpret that. The way that I prefer to think about it, more than a measurement, is if your particle strongly interacted with something. A detector is something that is going to trap the electron, or is going to interact with it electromagnetically by exchanging photons. That's what makes me think, whenever you have that exchange of a photon, that's what makes me think there was some sort of measurement that happening here. So if the hole is very big, and the electron is, the way that I imagine this, the electron is passing through, it will not interact with the edges, it will not interact with the thing. It's almost as if it passed through free space, or only the electrons that are going to be passing through near the edges will do anything, and that will be the minority, so you will not see the pattern on the other side. If the hole is relatively small, the electron, when it passes, has to interact with the walls, and that creates something in such a way that yada, 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 the pattern disappears. I don't fully understand it, but that's how I imagine it when I think about this. Make sense? Thank you for the question. Any other questions or comments? Laura?
Clarification on the experiment setup. The first time that they measured it without, when they just sent a stream of electrons, did they have that gap large enough that you can have multiple electrons going at one time, or was it just tiny enough that only one can?
I don't remember the details, but I know that afterwards, people did experiments where they were very careful in shooting an electron at a time. So that, because there were many explanations. And once this happens, everybody tries to come up with an explanation. And explanations that I think will make sense at the moment is, what if when you shoot the electrons all together randomly, they bounce with each other in such a way that that creates an interference pattern? And people, it's not that they postulated that, they did math to try to see if that will make sense. And that's kind of this type of reaction is exactly how I want you to think about this. Is there is an experimental observation that our experimental colleagues were able to bring to us, And now we have to think how we can develop a mathematical framework that explains this, and then that I can use to predict other stuff. The multiple electron colliding, that doesn't work, because I can make the same experiment really shooting one electron at a time and the same thing happens. Has to be something else. And I'm going to give a hint of another experiment, and then I'm going to show you the mathematical formalism, which is the classical quantum mechanical theory that we use to describe this, the second experiment that I'm going to mention, and many other things that we're going to learn throughout this course, because of course you're watching this video in order. The other experiment is called the Stern-Gerlach experiment, and basically what they did, they put, all of this was happening kind of at the same time. They put two very strong magnets. They have a very strong magnetic field. And you shoot, in this case, I think they were shooting silver atoms. Silver, what is the chemical? Ag. Okay, silver, whatever was the atomic number of the silver. They're shooting silver atoms to this thing, and the silver atom has an intrinsic spin. You can think of the spin as a tiny magnet that, in this case, they imagine it as an arrow. And if you have a collection of these things, you can think that this spin is oriented randomly everywhere in the angles in space. They shoot them in this way, and what they were expecting is that if you have one of these silver atoms whose spin is completely parallel, it will not feel anything. I'm almost sure that it was this way. That's it. Now I'm curious. I don't remember the details, but basically what they were expecting is that depending on the orientation of this thing, you will have a set of trajectories that will basically be a continuum depending on the original orientation of your spin, because certain orientations of the spin will feel a stronger force or a stronger interaction with the magnetic field. So they were expecting to see a blob on the other side, more or less populated with all the possible orientations of the spin that they have. That's not what they observed. What they observed was two fringes and nothing in between. It was like, that's weird. And if you calculate the position of these fringes, they perfectly correspond to if the spin was completely anti-aligned with the magnetic field or if the spin was completely aligned with the magnetic field. Those were the two options that gave you that spread. Nothing in between. And it's like, wait a minute, that cannot be. How come I have a gas of silver and suddenly everybody is either pointing up or pointing down? Up and down with respect to what? Gravity? No, that makes no sense. So they did a lot of experiments trying to change the orientation of the magnets, see if they had any systematic errors, and this was, I don't know how to write down Stern-Gerlach experiments. I'm going to put this. This was a Stern-Gerlach. So these two experiments, along with many others, leave us on the puzzle. What are we going to do to describe nature? And quantum mechanics was developed gradually by a lot of people. These postulates, and I'm going to explain in a second, come from one of my favorite quantum mechanics books, Tanucci. I also realized that I don't know how to spell Tanucci, but that's how I learned quantum mechanics. Strongly recommend that you take a look. I really, really like it. It's a very good book. So after years or decades of fighting and trying to come up with a way to explain this, we arrive at the following set of axioms or postulates or building blocks. These are the things that for the quantum mechanical modeling, we're not going to question. We can question them later, and we can try to find better explanations for things. You will see that, for example, at the end, we're going to arrive at the Schrodinger equation, and the Schrodinger equation is intrinsically not relativistic. It doesn't treat time and space in the same fully. So questioning that is what leads to creating, for example, the Dirac equation that can explain antiparticles and can explain a lot of other stuff. So definitely, you're allowed to question these. I'm just going to share with you. Right now, I'm going to show you the building blocks, and we're going to build stuff based on these blocks. The first postulate of quantum mechanics, this one here, is that at a fixed time t0, the state of any physical system is defined by specifying a ket belonging to a state space E. We're going to talk about state space and Hilbert space in a second, but basically what this is telling you is that previously you were thinking that you were describing physics, all the physics, if this is a marble that is moving around, you were describing it in terms of positions and velocities. In Newton's equations or Lagrangian mechanics, you're always trying to ask yourself, what is the position as a function of time of all the building blocks of my system? You have dynamical equations that tell you how that happens. For example, in the case of Newtonian physics, you write that all the forces acting on your particles is what is going to drive the dynamics of that particle. That is going to be the change in momentum with respect to time. And if your mass is conserved, that will be the acceleration of the particle. Yeah, makes sense. If your object also have orientations, you can write an equation for the torque, which is things that make it rotate, and that is going to be the change in the angular momentum with respect to time. This is in the classical sense. So the thing that describes your system is these positions and orientations. In the quantum mechanical sense, what this is telling you is that we're going to describe the state of my system as something that we call the wave function. Now, in many cases, this literally will look like a wave. Whenever we're talking about the electrons that are propagating in space and doing the interference pattern, you can imagine it as a wave. There will be other situations in where we're talking about discrete levels, for example, when we talk about spins, and I'm going to say the wave function of my thing, and it doesn't mean that it's a wave that is propagating. It's kind of a superposition between these two very weird spin up and spin down. So think of it as a wave, but don't marry yourself to the idea that it has to be a wave. We describe our system in terms of this wave function that basically I want you to think it either as a wave or as a vector, because we're going to be using linear algebra and vector spaces. So this is, if you want to think it that way, is an arrow, a red arrow that lives in a very abstract vector dimensional space, and things are going to happen to that arrow. And any question that you want to ask about the system, we're going to ask it to that arrow. So far, so good on what I'm saying? Interrupt me if there is some clarification that I need to make. To give you an idea, this is something that I got from ChatGPT a year ago, so you can see how it has improved ever since. It looks very weird, but I actually wanted to keep it. This weirdness, keep looking at it and you will find more weird stuff. I wanted to keep it this weird because this tells you, this gives that intuition of, yeah, nothing works in here. This is what I call the Hilbert space. In my case, I call it a Hilbert farm. You can see the Hilbert naming here. ChatGPT tried its best. And all of these things, I want you to think of them as these wave functions, different wave functions. This is psi1, this is psi2, and they live in this Hilbert space that looks extremely weird. And we're going to also call them kets. You'll see why whenever we talk about Dirac's notation. And yeah, I find it very funny. It tried to make like a sheep pig in here. It put some equations that I don't know where it got them, a bunch of numbers. So this is, when you were talking about intuition, it has this very strange wave. I guess it's because I was talking about wave functions that it got from this very famous Japanese painting. So whenever I think about the vectors that live in a Hilbert space, I literally think of this picture. And this is, to me, as intuitive as any other imagination that I can have. It's just a weird place, but that's okay. Okay, so that is the first postulate. The second postulate, every measurable physical quantity A is described by an operator A acting on this space. This operator is an observable. That means if you're talking, for example, about the spin of a particle, which we were imagining this as this tiny magnet, that is an observable. That is something that I can measure. I can measure the angle of the direction of a tiny magnet if I had it in my hand. I can measure how oriented it is. The postulate is telling you you have to transform that into an operator that acts on this Hilbert farm into these vectors. Since we're thinking in terms of matrices, this operator idea, I want you to think of it as a matrix. In many cases, it's going to be a finite dimensional matrix, which is the things that you're used to. In many other cases, it's going to be an infinite dimensional matrix. Other observables that you know, anything that you could measure out of a system, it doesn't have to be quantum, but can you give me one or two examples of things classically that you could measure?
Energy.
Energy, fantastic. This is telling you you need to find an operator that is associated with that energy. And in this case, this operator ends being the Hamiltonian. So energy, the operator associated with energy ends up being H, which is the Hamiltonian of the system, which makes sense if you have taken any course on classical Hamiltonian mechanics. The Hamiltonian of a classical system basically represents its total energy in most cases. Any other? Flora, do you have one? Position. a momentum of a particle, which end up being something that we call conjugate variables. And in the basis of eigenstates of position, meaning literally functions that they look as a function of x, that is what is something expressed in the eigenstates of position, the momentum operator ends up looking like a derivative. I think there is an I and maybe there is an H bar. I'm not sure about this H bar. Maybe there is a minus, but doesn't matter. The position, you no longer ask what is the position of the particle. You ask what is the position operator, which is going to be a matrix. In this case, it's a derivative, the derivative matrix. You know that because we have played with derivative matrices before. So it's literally the derivative matrix applied to your ket that lives in this weird dimensional vector space. Make sense? That is one of the postulates. The third postulate, the only possible results of the measurement of a physical quantity A is one of the eigenvalues of the corresponding observable A. You're going to have your operator that now we said is a matrix. I'm running out of space. So in here I have my operator, which is a matrix, n by n. If you have an n by n matrix, this thing is going to have n eigenvalues lambda. Let's call it lambda 1, 2, lambda n. These are the only possible results that you can get from making an observation or a measurement on the system regarding this operator. If your operator is infinite dimensional, then you have an infinite dimensional set of possible values. But this is a part of quantum mechanics that talks about quantization. You can only get a staircase of levels. You don't get a continuum of levels in many of these things. By the way, I'm telling you all of these rules, and this, as I said, came after years of trying to make sense of what was happening in the experiment. What I'm sharing with you are the key findings that we have found to work extremely well for many experiments. Does it mean that nature really works this way? Does it mean that nature really is quantized and the level of things are in a staircase? I see Lauren saying doing this. What do you think?
It depends on the degrees of freedom. Like a ball, if it could have, I guess, doesn't have. I don't know. It will work in some scale and break it at others.
What do you think, Lauren?
I agree with Ron. I think also like subject to change based on new findings.
So then let me summarize that. It's not that nature really works this way. It's that this is a mathematical framework. This is a model that we're using to explain certain aspects of nature. It will break under certain cases. But so far, the model, part of the assumptions of the model is that I'm going to have these operators with a discrete level of sense and measurables. Yep. Okay. Fourth postulate that comes in two flavors, depending if you have a continuum or a discrete thing, is basically telling you if you want to know what is the chance, what is the probability of measuring this specific observable in a certain state. Remember that we talk about the ket. So you have your ket, psi, and you're describing your system in that way. You know what are the possible outcomes of a measurement that you can have. By the way, I want you to think of that as a piano. Basically, for me, quantum mechanics looks more like a piano than it does like a violin. You have these discrete sets of notes, etc. Quantum mechanics sounds like instead of something like. The second is a continuous thing that you can do with a violin. The first one is discrete sets of steps. So you can either obtain this note or this note, but you cannot obtain anything in between. So once you have your system that is described by the ket psi, and you want to know what will be the different types of measurements that you can have, they are going to be described by the projection, and we talk about projections in the class when we were talking about normal modes in the math part, the projection of your state onto the eigenstates of that observable. So for example, when you have your Hamiltonian that we said that is the operator associated with the energy, and you find the eigenstates of the Hamiltonian, you're finding the energy levels of your system. And once you have your given system in any particular configuration, doing the projection on that basis of eigenstates will tell you the probability of measuring this energy or this energy or this other energy and so forth. That's why in quantum mechanics, most of the time, whenever we're doing anything, we're trying to find the eigenvectors and the eigenvalues or the states of the Hamiltonian. Make sense? In the case where you have something that is continuous, well, it doesn't make any sense to talk about the probability of measuring this value. You have to talk about the probability density. So that's why you will multiply by this alpha, because measuring a specific thing is the probability 0, but then you can make an integral over a specific range. The final two postulates, very important. Fifth postulate. Once mathematically you make a measurement out of your system, that means you do a projection on one of the states or make an expectation value with an operator, the wave function of the system collapses to the state that gave you that measurement. So for example, if I have in my piano, I have this, let's say between here and here, I have these 12 notes. I have these 12 notes that I could measure. And after I perform a measurement, I obtain an F. I cannot sing an F. I don't have perfect pitch, but some people in the audience might know how an F sounds. The wave function immediately collapses to the eigenstate associated with this energy. And then it will propagate in time and it will do other crazy stuff. And if you measure again and you obtain this, because the system continues to interact with its environment, then the wave function will have collapsed to that. And the final one, and that's what takes us to the Schrodinger equation, the way that we do dynamics in quantum mechanics, the way to understand how the system propagates in time is given by the Schrodinger equation. And the Schrodinger equation tells you that the time derivative of your wave function is going to be proportional to the energy operator, the Hamiltonian, acting on your wave function. This took Schrodinger a long time to derive, and the inclusion of this I is a very interesting social situation because he was not very happy of including that in there. Like, that makes no sense. What do you mean that nature? Does it really mean that nature works in complex numbers? That question to me makes no sense because this is a model, but they felt very uncomfortable by the fact of they having to add this I. The reason to add this I is because complex numbers that we discussed before, and I wanted to make a mention in here, if you have the imaginary axis and the real axis and you have a complex number C, you can write this as A plus IB. This will be the Cartesian representation of the complex number in where you have a real part, this is A, and you have an imaginary part, this is B. You following me so far? But you could also write this as in polar coordinates, a distance r times an angle theta. And this e to the I theta, if you were to write the representation of this, and you can convince yourself of this by solving the differential equation or expanding in Taylor series, this e to the I theta is equal to cosine of theta plus I sine of theta. So the combination of this with this basically gives you the decomposition, the polar decomposition of this vector in terms of this complex number. So the complex number e to the I theta, as you're changing theta, this is basically an arrow that is doing this, that is rotating around in the complex plane. If you end up describing a wave as e to the I kx minus omega t, this is a wave that, if you were to look at this is x, is a wave that is basically doing a spiral, is propagating in x and in time, rotating in this way. And that seems to be just the perfect language to describe quantum mechanics. Quantum mechanics talks about waves, and wave propagations, and wave equations. Sometimes the quantum mechanical objects act in a diffusive way, meaning that they spread out. Having that I that makes you rotate and spread out is the perfect type of description for the things that we want to obtain. So that's why Schrodinger put that I in there. And once you take into all of these postulates, by the way, I think I didn't put any emphasis on this, friend. This projection, beware that there is a square, modulus square here, that tells you whenever you have your wave function, it's going to be a complex value wave function. Observables are real. If I measure the energy of a system, I get 7 mega electron volts. I don't get 7 mega electron volts plus 3i mega electron volts. So the observables have to be real valued quantities. So to achieve that, whenever you get your wave function, you're going to usually square it, take the modulus square of the wave function to calculate anything that relates to the observable. So you can think that in the case of these experiments, the wave function of the electron, psi, is propagating as a wave, is making this interference pattern, but whenever it touches the detector and interacts with the detector, it collapses, you square the amplitude. That is what it's going to tell you this pattern of the chance of the electron appearing in this way. That is what allows the electron to behave both as a particle and as a wave. It propagates using a wave dynamics, but whenever it interacts with matter, it interacts as if it were a particle, and that has to do with the collapse of the wave function. Final thing that I say on this, and then we're going to probably take a 4-minute break. If you look at the Schrodinger equation, I'm going to write it in here. I h bar via dt psi. This is equal to h psi. I'm going to pass this I there. Via dt of psi is equal to minus I over h bar h. I'm going to put all of these in a different color. Psi. I ask you to, what is the solution to this differential equation? I have a function that I make one derivative with respect to time, and I get the same function multiplied by this whole mess. Right? Isn't the, if I were to ask you, I have f prime is equal to lambda f, wouldn't you say that f of t is equal to some amplitude e to the lambda t? Well, you just grab whatever is sitting in here, and you don't think, and you write it. You say, okay, cool, psi, then as a function of t is going to be e to the minus I h over h bar t. And then you have to put some amplitude. Well, turns out that this thing actually also depended on x. So what I'm going to put in here, I'm going to put psi of x t equals 0, my initial condition. And this friend is called the evolution operator. In case you have seen it in textbooks. And it comes naturally by realizing that this is a differential equation of an exponential, with the problem now that you're doing e to the matrix. And then you have to think, what the heck is e to the matrix? But if you were able to decompose this function into a linear superposition of the eigenstates of the Hamiltonian, then whenever this h is going to act on this friend, the h is going to behave as a number, as the energy associated with this particular eigenvector. So whenever you do the e to the minus I h bar over t, sorry, no, not over t, what am I saying? H bar t acting on, let's say, phi 1, this is going to be equal to e to the minus I, the energy of that eigenstate, because that is what that's what it means that this is an eigenstate of my Hamiltonian. And now this is just a complex number rotating, as we said. And what will happen is that all of these friends are going to start rotating with different energies, and that is going to create this interfering pattern. That's how the dynamics of this thing is going to evolve. That's another reason why we're very keen to try to find eigenstates for the Hamiltonian, where the Schrodinger equation that we're trying to find, solve now, is what people call the time-independent Schrodinger equation. I prefer to think that there is only one equation. This is this Schrodinger equation. And this is the equation that I used to try to find the eigenstates for that equation. But I don't, that name doesn't ring a bell as good as saying the time-independent Schrodinger equation. Time is still here. It's just that it's a trivial rotation by this complex. Okay, I have monologue for a lot. I really thought actually that I was going to be able to finish this in less than an hour and a half. So what we're going to do right now, we're going to take, let me stop sharing here. We are going to take a 4-minute break, so that gives me time to gather my thoughts on what are the next things that I want to say in the next half an hour. People on YouTube, make sure to take a break and walk around and stretch your leg. Same for people here in the room. And I will see you in 4 minutes. So far, so good? Helpful? Okay, and we're back. Now, what we're going to do, we are going to play for a little bit with this mysterious magic box that I have in here. So basically what we're going to do, I'm going to turn this thing on. Once it's on, it's going to be very noisy. So I'm going to explain most of the things now, and then we're going to look at it together. But basically this rope is going to start rotating, and it's going to start forming patterns. And among the patterns, there will be moments in where it forms this perfect resonant mode or normal mode that I have talked about before. I think in the first math lecture, you saw us playing with that with a specific rope. So it will form these modes. And the idea is what I want to transmit to you. Actually, I'm thinking, could it be that we use this exact same box? Well, if this is the second time that you have seen this box, you now realize how important this concept is. So the main idea that I want you to take away is that whenever you're thinking in quantum mechanics in terms of this ket, this wave function, most of the time you're going to have something crazy that is evolving in time kind of randomly as it's propagating through space. But whenever we're looking for the eigenstates of a specific Hamiltonian, we're looking for this normal mode. They're going to come in discrete levels, and they're going to be, once you have them, the time dynamics of them is trivial. They're just going to continue being rotated in that way. So let's try to see if this works. Okay. So amazing how many things can go wrong when you're trying to make this. Hello. What happened in the video that you are watching is that the background was not dark enough, so we couldn't see the rope. So everything that I said before turning the machine on still holds true, but I'm going to turn the machine on right now, and we're going to see all these normal modes being made here. Let me do it. So you see this random behavior, but in certain conditions, you can have the mode with 1. That would be the first normal mode or eigenstate. Okay, there we go. This will be this one with 2. And depending on how you hold it, you can achieve the one with 3. Try to do the 4. There we go. I'm going to try to do 5. Well, it's difficult. Let me see if I can make one with maybe. So you go, David. Thank you. Thank you. So that's what I want you to have in your mind whenever we're describing these things. Mathematically, once we diagonalize the matrices and find the eigenvectors and the eigenvalues, the eigenvectors are going to be these shapes that are resonant. How the shape is will depend on the Hamiltonian that you're looking at. We're going to look at that in a second. But at the end, that's basically what we're after, finding these normal modes. And then the energies are going to be associated with how quickly this thing is rotating. In this case, I think this is always rotating with the same frequency because I have it such that is a motor. But in the more general case, think that the more nodes your wave function is going to have, the faster it's going to be rotating. Okay. let me put this back. So, are you with me? Okay, so we play with the rope, and I hope that that drove the idea of how, at least I imagine quantum mechanics as these waves. Once you write the Schrodinger equation, what will usually change from system to system is the Hamiltonian. This is what I like to call the rules of the game. Most of the time, this is going to be equal to a kinetic energy plus a potential energy, and the kinetic energy, because of how the derivative operator, the momentum operator becomes a derivative operator, will be equal to minus h bar square over 2m d at dx square. This is basically same p square over 2m. It's the same as b square m 1/2 in the classical sense. And then the potential is usually what you change whenever you want to describe a different system. For example, if we were interested in describing, as we were talking at the beginning, the hydrogen atom, the electron orbiting the hydrogen atom, which is fundamentally a quantum mechanical system, what would be the potential energy of that electron? Any ideas? What is the forces that the electron feels?
Force?
Yeah.
Or energy?
Potential energy that then creates a force.
Oh, in the, sorry, can you repeat it?
Yep, I have the hydrogen atom, electron, orbiting a proton. I want to write the Schrodinger equation for the hydrogen atom. The kinetic part is going to be relatively straightforward. It's going to be p squared over 2m, but now this is going to be a 3D momentum, which is going to become the Laplacian, which is derivatives in 3 dimensions. What should be the potential term on the hydrogen atom?
Coulomb.
It will be the Coulomb force. So I will have to write something that is proportional to 1 over r, proportional to the electron charge, proportional to the 1 over 4 pi epsilon 0. Yeah. So this is basically the Schrodinger equation for the hydrogen atom. You will have that Laplacian, and it will have the potential term. And now your task is to find what are the resonant modes, the eigenvectors and eigenvalues of this Hamiltonian. And that takes a long time. Actually, that's the class that I taught last week, because we're doing this out of order. And there's many numerical techniques for how to solve this. But at the end of the day, I want you to think that you come up with these rules of the game, this potential, and you're trying to find these resonant modes of that thing. That resonant modes for the hydrogen atom in the angle part is going to become what we will call the spherical harmonics, which are the solution to the Laplace equation in spherical. Details don't matter, but that spectrum is also going to give you the piano, the tunes, for the frequency that the hydrogen atom shows you, which is something that actually you can see experimentally, that the hydrogen atom has specific spectral lines if you were to plot this as a function of energy, the different nodes that the hydrogen atom can give you. For example, if we're going to play with this today. If you were to make the potential an infinite square well, a box in where the potential is infinite, and then it's 0, and then it's infinite again, that will make a specific Hamiltonian that you have to solve, and you will obtain the eigenvalues and eigenvectors of your equation. If you want to describe tunneling, if you want to describe the harmonic oscillator, if you want to describe a particle orbiting in a magnetic field, if you have a charged particle classically in a magnetic field, you will start doing circles. In quantum mechanics, you have levels of these circles. You cannot choose any circle. It has to be a circle such that the particle kind of closes and comes back in the same wave. It has to resonate. And those are called Landau levels. And that appears whenever you're describing quantum mechanical particles in a magnetic field. You want to describe spin levels, the Stern-Gerlach experiment that we were talking. So every time that you have a different system that you want to describe differently, as a physicist, what you will do, or as a chemist, what you will do is change the Hamiltonian, change the rules of the game, try to make those rules as close as possible to what you think is happening in real life, and then solve the differential equation. Obtain your spectrum, compare to real life the energies and the wave functions that, or the probability distributions that you can obtain. If it matches, feel very good about yourself. If it doesn't, feel very, very good about yourself, because that means that there is more work to do. So there is more math to do in the future. Does that make sense? Any questions with respect to that?
I have a few questions, but I'll probably leave it before. In classical mechanics, you have these concepts of, let's say force, something like that. But in quantum mechanics, it seems like we only care, like the idea of force is not as mentioned much as something like potential, which, well, one kind of like in classical, force would be a vector and potential would be a, let's say, a number. Is there like some kind of intuitive understanding why we're not, like, what one cares about is like these number in classical mechanics, or these and what is so that's it.
The intuition comes, this is a very, very good question and perfectly embedded into the whole series of lectures that I am making. If you watch the videos on classical mechanics, actually last class, the previous to last class, we started talking about Lagrangian mechanics. And basically what happens is Newton comes into the stage, writes the equations. People start doing classical mechanics by modeling forces. This whole thing that I said about the rules of the game, blah, 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 in classical mechanics is what are the forces that are acting on the particles. And for example, one huge discovery is to realize that the force of gravity is proportional to the product of the two masses and inversely proportional to the square of the distance. That is huge. It's like now you know what is the force that Jupiter feels because of the sun, and the moon feels because of the earth and because of the sun. And once you have those forces, you can write everything on all your dynamical equations and try to solve. Are you with me so far?
Yeah.
Okay. As you start complicating the systems that you want to describe, this idea of the forces becomes a bit murky, especially if there are constraints in your system. If you start talking, for example, this is a bit of a digression, but it's a very good question. If you start talking of a particle that is moving inside a cone, what forces are acting on this particle? Well, obviously gravity and the normal force, and maybe friction if the cone has friction. But the normal force, you don't know exactly what is the normal force because it depends on the movement of the particle. If the particle is just standing there, it will be some angle with gravity. But if it's taking a turn and accelerating, the normal force will have to be bigger. So the value of the force depends on the solution, but the solution depends on the value of the force. So you end up having this problem of like, what do I do? Because of this and many other reasons, people started seeking for alternative descriptions to classical mechanics. And one of the first things that appeared is called the Lagrangian mechanics. And in the Lagrangian mechanics, instead of talking about forces, you talk about building the Lagrangian of the system, which in many cases ends up being equal to the kinetic energy minus the potential. And from the Lagrangian of this system, which represents intuitive many things, is kind of complicated to think about it, but you can write something that is called the Euler-Lagrange equations, which requires that the action, which is the integral of the Lagrangian with respect to time, is stationary with respect to the physical path that your particle tracks. This gives you the Euler-Lagrange equations that look like this. Details don't matter, but you end up obtaining equations of motions to describe your system in terms of its generalized coordinates. The generalized coordinates doesn't have to be positions. They can be anything. It can be the length of a rope. This becomes the thing that gives you your dynamical equations once you have plugged in a value of the potential energy. See that now the question is not what are the values of the forces, it's what are the potential energies in my problem and how does the kinetic energy term look at as well. A bit later, Hamilton created Hamiltonian mechanics, in where instead of talking about the Lagrangian, you do what is called a Legendre transform to the Lagrangian. Details don't matter. You end up with something that in most cases looks like T plus V. And from here, you write what are called the Hamilton's equations of motions, which now instead of describing things in terms of Q and Q dot, you describe them in terms of P and Q, which are conjugate variables. Q is a generalized coordinate and P is a generalized momentum. It's not Q dot, it's something else. And the equations of motions that you get look like this. They're equivalent to the Lagrangian equations. It's just that you end up with two first-order coupled differential equations instead of one second-order differential equation. So far, I haven't addressed your question, but this is the story of what happened in classical mechanics. In quantum mechanics, when we are trying to make the transition and we're trying to say, what do we do? If you try to talk in terms of forces, usually the concept of force, we acted on a specific point in the particle. Even when you have a composite object like this, if I'm talking about the force of gravity, you can think that gravity is acting on every point of this thing down, But if you want to model that, you can say, oh, gravity is acting on the center of mass. It's acting on that point. And if I do something like this, that would be a huge impulse force that I made in this thing that made it rotate, etc., etc. You have a wave function. The electron is a wave function that is everywhere. Force where? Where is acting? How does a force act on a wave? I don't even know how to think about that. So this on its own, problematic. I don't even know how to start talking in terms of forces acting on a wave. If you try to do it with the Lagrangian, something else fails. I don't remember exactly what, but there is a couple of things that don't quite add up, at least at the beginning. Later on, whenever you try to generalize things to special relativity, and you give birth to something that is called quantum field theory, we come back to Lagrangians, and instead of talking in terms of Hamiltonian, you write about the Lagrangian of the field of particles, and it's quite interesting things. The Hamiltonian, being the operator, being the quantity that is associated with the energy, played the perfect role to become the operator that is associated with the energy, and the energy is one of the most important observables that we're interested in. So because of this whole long story, and thank you for the question, it's a very good question, we end up describing at the beginning quantum mechanics in terms of Hamiltonians. Hamiltonians talk in terms about potentials, not forces, which is a good thing, because that way you don't have to think about the force acting on a part of the wave. Does that make sense?
Yeah, it makes sense.
Excellent.
And also, it kind of like I was thinking about exactly that when you talk about the field theory. I kind of like I don't know, like a simple way to think about how these potential might act on these objects is like think of it as field. I get there may be some of the why start thinking about those like the thing like
this V is an operator. It's a matrix. As a matrix, it acts on a vector. It touches every part of the vector in some defined way. I don't know how act with a force on this vector that is very high dimensional. Yeah, that's it. Make sense?
Yeah. Thank you.
Excellent. No. Thank you for the question. This was great. Okay. Any other questions? So does it make sense? What is your role as a physicist and a chemist? A scientist. You sit down, you have your physical system that you want to describe using quantum mechanics. The question that you need to ask first is, what is a good Hamiltonian? Most of the time, what is a good potential interaction between these parts of my system? And you invent it. Whenever you come up and you say, for example, for nuclear physics, a Hamiltonian of blah, blah, blah is this Kern density, you're making that up. That comes out of your imagination. Not even when you write down the Coulomb force. Is that really how electron interacts? I don't know. The Coulomb force in particular acts infinitely fast. You feel the 1/r regardless of how much time it takes for that to propagate from one place to another. So if you want to make something relativistic, you need to talk about something that are called retarded potential, and it's a whole mess. But the point that I'm trying to make with that is that all of those Hamiltonians are made up objects that you decided to make in order to model your system. That is the first step. After that first step comes the math. Once you have come up with a form for your Hamiltonian, it's your responsibility. You brought it into the world. You better take care of it. You better feed it. You better take it to go potty, etc., etc., etc. You have to solve the Schrodinger equation. That most of the time is extremely complicated. There are some techniques, some of which you will learn, some of which the computer will take care of. Okay, before, let me see my very glad magic box break activity. Okay, before we do the activity, which will be very short because we're running out of time, I want to talk about Dirac's notation because it's just brilliant piece of notation. Genius, yes. I made this summary.
Now I think of vectors and like operators, matrices, and vectors in terms of direct notation.
Oh, definitely. There is no way to think it. Like once you see it this way, it's like okay.
Like basis transformation, all of those.
Yep.
Much easier.
Yep. So this is my dog Dirac. So the person that made this, in case you have seen my dog and you're confused and you're thinking that this is a notation of my dog, no, Dirac on the left. My doggy didn't make that, but his name is Dirac. So the way that I want you to think of this, remember, this is your cat that lives in that very weird Hilbert ChatGPT generated farm. Most of the time, you're going to be thinking of this as a wave, as a function of position, x. You're going to make a drawing that looks like that. If I'm describing something with spins, it doesn't look like this, but I'm still going to think of this wave in some way. If you're talking about a function, you can always discretize your space in tiny pieces. That is what computers do. Computers don't think of continue value stuff. They discretize it. And then this ket becomes a list of the values of the function on those locations. This basically becomes a very long vector of dimension big N. N is the number of points that you have. And I want you to think of this as a piece of bread that has peanut butter. No, peanut butter. That will be the ket. A bra, you obtain a bra whenever you flip this thing around. There's other ways that you can obtain this thing, but I'm going to talk about these ones first. And if you want to think of this is bra. You can think of it as a function in the same way as before, but you have to put a complex conjugate. And it just has to do with the fact of complex numbers being the way that they are. For us to obtain real numbers out of dot products between these two things, we're going to define that a bra is the same as a ket, a transpose, and with a complex conjugate. That transpose means that in the notation that we're following, instead of writing it as a tall column vector, I'm going to write it as a long horizontal vector. And I want you to think of this as a side of bread that has jelly. When you have a bra and a ket, you can make this funny thing that is called a bracket, hence the notation. And this is basically the dot product or the projection between these two vectors. If you have watched the math videos that we did before, this is telling you the shadow that one of these things is casting upon the other. If you define them as functions, the dot product between functions is an integral, and remember that we need to put the complex conjugate on the bra. If you're talking in terms of vector, it's a dot product between vectors, which you know how to do. Entry by entry, you multiply them and you add them all together. And that is a sandwich. In this notation is basically you grab peanut butter, jelly, splash. And that is your sandwich. And we literally talk about in physics about this as a sandwich. You will see that in many books. Finally, nothing is stopping you from placing an operator in between these two things. If you think that this operator has some functional form, for example, it could be some derivative, it could be multiplied by a function, it could be something more complicated, but this bracket with an operator in between, you will define it as the dot product with the operator acting in the middle of these two things. Be careful because sometimes these things don't commute. It's not that you can place the h to the other side. And if you're talking in terms of the matrix notation, well, this is your vector psi, this is your vector phi, and this is your operator h that you're representing as a matrix. And in binary matrix, you make all of this, and this gives you a number, which is the dot product of these two bracket and ket through this. And to me, that's equivalent of putting, for example, a banana in between the sandwich. Yeah. Any questions? Extremely good notation. Okay, so in the next 10 minutes, we're going to solve our first quantum mechanics problem. Let me see that I think is the last thing that I have to. We're going to do it together. And I want your help. So usually, here's what we're going to do. In the class, usually we have an activity and I let the people do it for like 5-10 minutes and I shut up and they try and then we come together and we talk about it. Since I really don't want this video to be way longer than an hour and a half, I will ask people that are watching us in the posterity to pause the video at this moment and try to solve this problem by your own. And then you can continue watching the video as me, Lauren, and Anne solve it in real time in the next 10 minutes. This is an infinite square well. The potential of this Hamiltonian is given by a step function. The value of the potential is infinite in this region, is infinite in this region, and is 0 in this region. So we have to solve the Schrodinger equation, what people will call the time-independent Schrodinger equation, where I'm looking for the eigenstates of this Hamiltonian. So you're watching on YouTube, pause, and come back after trying it. I'll be waiting. I assume that you're back, and now you can hear me, Lauren, and Anne solve this. How do you think we should solve this? What are your thoughts?
First, we have to plug in D in each region.
Okay, so I like that idea. Let's call regions 1, 2, and 3, because my potential is a piecewise potential. Why try to solve the whole thing when we can divide it into 3, divide and conquer? Yeah? The thing is still recording, right? Sometimes my phone will turn off. It will be very annoying. Okay, in region 1, what happens? Potential becomes infinity. So if I plug an infinity here, and the wave function is any finite number, by the way, the same thing that happens with Dirac delta functions and Heaviside and if it makes you uncomfortable to think of a infinite potential or something that is completely discontinuous, think that the potential is not that it's infinite, it's very, very tall, comes back to 0 and then goes up, and then it's very, very tall there. And I'm taking the limit as this height goes to infinity. So that every step in our imagination, this is finite, it's just that it's going higher and higher. So if I look at the Schrodinger equation, and this thing is becoming very, very big, the only way that I can have something that will not blow up and not makes a bunch of nonsense is if I make my wave function 0 on that location. If psi is 0, 0 times something very big, 0, this is 0, this is 0, and everything is satisfied. So what do you think should be the solution to the Schrodinger equation in region 1? Big 0. Excellent. Sorry?
I just want to
Yes.
say, so I feel like I remember Lauren's questions about like intuition of quantum mechanics, and there'll be I think circumstances in which you can kind of like have some classical picture.
Yep.
So like for example in this one, if you're in a region where the potential is very big, which is like kind of like something you cannot cross. If your wave function is 0, you can think about classically. That would mean that you cannot enter that region.
Yep.
Which makes sense.
It's
so
reality.
there's like always some like classical. Sometimes you have some classical picture.
Yep.
Intuition,
Yep.
and then you can kind of build the intuition in
Yep.
quantum mechanics.
Yep. The way that I imagine this is I have a finite potential, big but finite, and I already have some sort of lump as my wave function, and I'm increasing this. So basically all the wave function is pouring into it. Any wave function that was outside, I keep increasing the cost of living, making it harder and harder for anybody to rent any house outside of this thing. Eventually everybody just comes to the place that is not as expensive. Does that make sense?
Pablo,
yes.
I have a question.
Please.
If your wave function is just increasing in that potential, then there is still a tail end that, because it is a wave function, is there any possibility that the particle can actually get into an infinite well, or
if
outside of the infinite well?
So I am assuming that this extends all the way to the left, and this extends all the way to the right. So it's not a tunneling thing. It's more like it's a desert. Imagine it as inside the region, you have water and food and comfy and friends. As soon as you cross, there is no water, there is nothing. It's like the harshest desert ever, and it extends all the way up to infinity. You're not going to venture there. You could think of a situation in where if you put the wave function not in an eigenstate, the thing for a very big potential, but not infinite, the thing is kind of wobbling around and part of it will enter the barrier, spend some time in there and come back. But after an infinite amount of time has happened, I'm looking at the normal modes, those modes that don't change with respect to time, that are just there and exist and don't move. Any such solution cannot have any component inside of the well. It will have died out already, as we took the potential to be infinitely big. That helps? Thank you. So in here is also, in region 3, also 0. For the same arguments. You with me? I want to hear a yes.
Yes.
Yep. What about region 2? What is the Schrodinger equation for region 2? Can you tell me? Minus h bar square over 2m psi prime prime. What happens to the potential?
0.
So I don't put anything in there. This is equal to E psi of x. Rearranging this, psi prime prime of x is equal to 2m e h bar square with a minus psi of x. What is the solution to this differential equation? I have a function that I take two derivatives and I get the same function multiplied by minus a number. What is the solution to that?
It's exponential of the square root.
Sines and cosines. If you put exponentials with an imaginary term, yes, because exponentials and sines and cosines are the same function. They're just out of a phase in the complex plane. But I want you and everybody watching, whenever you see a differential equation that is two derivatives equals minus a number times the same thing, I want you to scream sines and cosines, ways that are doing this thing. Yep. Because the derivative of sine is cosine, the derivative of cosine is minus sine. So 2 times the derivative of sine is minus sine. Yes? Any questions, any doubts? Do you believe in this? Okay. So the solution of this is sines and cosines. So we're going to write it that way. Psi of x is going to be equal to a sine of something plus b cosine of something. What is that something? I'm going to have an x, of course. What goes in here?
Square root.
Since I'm going to take two derivatives, that whatever is inside is going to come twice. And once it comes twice and it multiplies itself twice, I get the 2me over h bar squared. So that something has to be the square root of 2me over h squared. Yep. Lauren, you good?
Yeah.
Okay. But let's look at the function in here. So if I look at cosine, cosine starts here and then starts doing whatever oscillations that it wants. The problem is that the wave function better be continuous through the entire Schrodinger equation. I have a Schrodinger equation that talks about a second derivative. The second derivative is already not continuous because you have a non-continuous potential. The first derivative is also not going to be continuous because the discontinuities in the potentials are infinite. The normal function better be continuous, or this entire thing is going to blow up. All of this is to say, I don't want to have any cosines in my function because that will imply that the wave function, put it in green, has a value here and then drops to 0 in a discontinuous way. So I'm going to drop the cosine term and I'm going to only focus on sines. So my wave function has to start as a sine. Does that make sense? For the same reasoning, that sine better be 0 here. This is what is going to give us the resonant condition. My sine function cannot have any frequency. I cannot have a sine function that does this. That will be a problem for the same reason that we were discussing. It could do this. That will work. It could also do this. That will also work. And the next one, and the next one. And you see the pattern that we were seeing with the rope emerge. You can have one node, you can have two nodes, you can have three nodes, you can have four nodes, and so forth. Mathematically, how can I find the condition for that? What am I after? So psi of x equals 0 should be 0. From here, we get that b is equal to 0, that cosine term. How can I obtain a condition for the frequency of oscillations based on what we were saying on the other end?
X equal to L.
Excellent. For the same reason, right? Okay, that means that a sine of square root of 2me over h bar square L is equal to 0. This amplitude doesn't matter. When is sine equal to 0?
Pi.
Every pi. So if this whole thing were to be equal to n pi, where n is any natural number, positive or negative, let's only focus on the positive ones because the negative ones just multiply the sign by a minus. I will have what I want. So that tells you, if I write that equation, I'm going to make elevate everybody to a power of 2 so that I can get the energy out of that. I get 2mv over h bar squared is equal to n squared pi squared. That means that the energy levels of these things, the resonant frequencies, the tunes, the go as n squared pi squared h bar squared over 2m. I'm missing an L. Where is my L? L squared. 2m squared. This is one of the results of that. If you have a particle in an infinite box, the energies goes as n squared. That means you have an energy for the ground state. The next one is 4 times as big as the ground state. The next one is 9 times as big as the ground state. The next one is 16 times as big as the ground state. This is the spectrum of the infinite square well. So my final question to you, and with this we're going to close. Suppose that you make an experiment, you have some molecule, something, and you measure the spectrum. Here is the energy, and you measure a line here, some unit, let's call this E0. And the next line is here at 4 E0 approximately. Is that okay? And the next one is way up here at approximately 9 E0. And you're measuring this out of the lab. What is your conclusion?
There's a high chance that this molecule is subject to a infinite square well, or like you can model the introduction of this molecule and infinite square well.
I'm very glad that you at least said model and you didn't say that, oh, I have a molecule that has an infinite square well potential. That would make no sense because you know that that cannot happen. What can happen is that if you were to look at a good model of what this particle is feeling as a function of x, maybe the potential looks like something like this. Very complicated, can have many things, but there is a region in where you start having this spectrum for a bit. Eventually, I don't know, after here, the wave functions start doing something crazy, more subject to this more realistic potential, but for a window of energies, you're able to describe this relatively well with a potential that is flat, rises very quickly on both sides, and the ground state sits, and the next excited state sit well below where the potential starts making any complicated things. That's how I would like you to think as a pair of physicists on this thing. I think that's all that I wanted to talk today. Any questions, friends, or any final comments? And we didn't do that bad on time. I think actually we did exactly an hour.
I actually really like that last explanation. I think that should be like I think oftentimes in quantum classes, we're just given the infinite potential well without much of an explanation of why the problem is presented that way. But looking at it experimentally, I think that gives you a much more like simplified thinking of, oh, this is why we're modeling it this way.
Thank you, Laura. That's exactly the reason why I explain why we go through the trouble of analyzing the harmonic oscillator. When you have the quantum harmonic oscillator and you say, I have a potential that is proportional to x squared, and then you obtain the solution. The solution is, the first one is a Gaussian, the next one is a Gaussian with some spices and so forth. These are called the Hermite polynomials. And we go over, I spend an entire video, I will spend an entire video in the future talking about the quantum harmonic oscillator. But one of the main reasons why we study this, not only because it's a good exercise, but because in nature, you may have molecules or other system whose potential is never going to be a harmonic oscillator, but might have a shape like this. It will have a minimum. And around the minimum, you can expand this with a parabola. And the first few states might be well described using the quantum harmonic oscillator machine. After that, it becomes very complicated, and you need more math, but that is the same reason why we might be interested. Thank you for the observation and the comment. Any other comments or questions before we close?
Well, I don't know too much, but what I've seen before, like in real research, like you would kind of usually there's some way to solve a complicated problem is to, let's say, expand the wave function in terms of the wave functions for the sake of a hydrogen atom, which is a simple one you can keep track of, and you're just kind of like trying to find the coefficients, which of those. Is there like an analogy where you kind of like look at the potential and expand the potential and kind of like solve, I don't know, for each potential you would have some solution to it, and somehow the total solution is somehow the linear combination of those things that you find?
Yeah.
Is there actually like in
Yeah, of course. Yeah, of course there is. The idea in this case, for example, will be you will say, and actually this is what my next class in quantum mechanics tomorrow, maybe, I haven't prepared yet, so I don't know. But one of my next classes is going to be about perturbation theory. And the idea in perturbation theory is you say, the real problem that you want to solve in here is a black potential. This is the harmonic oscillator potential. Are you with me, Anne? The idea in perturbation theory is saying, what if I told you, no. My original potential was the harmonic oscillator potential, and to that I added a perturbation where lambda is small. Who is this perturbation omega? This is going to be equal to V of x minus VH over. The difference between this parabola and the black curve. See that if the parabola fits very well the black curve in the center, this difference is going to be mostly zero around that center, and then it's going to start deviating. And you can treat that as that is your perturbation, and what you're trying to answer is what happens to my ground state and my first excited state as soon as I'm starting to pay attention to this perturbation. But it's the other way around. This was the original thing, and this is just an intermediate state that you're trying to use to be able to say anything about the problem. In this case, that is the analogy to what you're asking is you're going to treat this difference. You already know how to solve this potential, so you're going to, if you choose a potential that you already know how to solve, and it's not that different from the thing that you're trying to solve, you can treat the rest as an expansion. So yeah.
Yep.
In nuclear physics, that happens a lot too. If you try to, I don't know if you have seen my theory talk, but when I talk about nuclear theory, I talk about the shell model and trying to come up with the spectrum of the magic numbers. And the magic numbers for nuclear physics are 2, 8, 20, 28, 50, 82, and 126. And if you were to model the nucleus as a harmonic oscillator, because you can, because we know the math, you obtain as magic numbers. It's 3, and you're like, ah! But the next one is 40, the next one, I don't remember, maybe 80. They start deviating. So that makes you realize, you probably cannot treat the nuclear potential as a quantum harmonic oscillator. And after you think for it for a while, it makes sense because the quantum harmonic oscillator will look like this. And you know that the nuclear force saturates. It doesn't grow unbounded later. What do you do? Well, that is one of the first things. And the second thing is that it saturates, meaning that near the center, it should look relatively flat. Instead of a parabola, you expect something that looks more like this, which is a Wood-Saxon potential. And the first math that people did with this, what they did is they used a harmonic potential and a perturbation that modifies the harmonic oscillator potential a little bit so it looks more flat in the bottom and it doesn't extend up to infinity later. And when you add those corrections, this is the magic numbers that you get. And you're like, yay! Does that mean that nature really works in that way and the nuclear potential is really a Wood-Saxon potential? No, that is but a model that we use to describe what is happening to protons and neutrons. Okay, so with that, these were fantastic questions. Let me stop sharing this. Oh, you have a question. Please go ahead.
I guess on a more philosophical level, at what point can you, I think your answer will be you can never confidently say, but at what point can you more or less say, oh, starting now, we are just applying an expansion correction versus, oh, we need to start introducing a new model for this phenomena or area?
There's two ways in where I think this. There's two main reasons that I can think that may happen. The first one is you can be in a situation in where you cannot reach the new insight by small perturbations. It might happen that the new thing that you want to add requires building up from scratch. For example, both the electron in the atom and the protons and neutrons inside the nucleus feel forces that are very important. They're called spin orbit forces. And it's basically the coupling, the interaction between the intrinsic magnetic field of your electrons or protons and neutrons with the orbit that they are tracing. You can think of it as an electron doing this is a charged particle. So classically, it's almost as if I had a current of charge that is doing this. That will generate a magnetic dipole moment. That dipole moment can interact with the dipole moment of the electron on its own. So that spin orbit interaction plays a role in that. If you want to model that better, it's easier or is more correct if you do it from a relativistic point of view. That requires that you write the Dirac equation, and that is much more complicated. But you can add the spin orbit term both to the hydrogen atom and to the nuclear physics part as an ad hoc term that you say, I'm adding this as a perturbation because I think that this will work, and it will work, and it will help a lot in making a Schrodinger equation that takes into account better what is happening in there. So that is an example in where you can fix things a little bit by adding a term. I need to think of an example where that doesn't happen, but anything that has like complex functions that have like branch points or divergences, or if you're doing a Taylor expansion, for example, if you're doing a Taylor expansion of the logarithm function, the logarithm function diverges near 0. You know how the log function looks like. So if you make a Taylor expansion around x equals 1, log of 1 is 0, you can make a Taylor expansion, you get something. It's like 1 minus x plus x squared over 2 minus x cubed over 3, so something like that. I don't remember the exact, but you can make it. If you make that expansion, you can do the perturbation, which means a Taylor series, around that value and obtain values for nearby x's. As soon as you make the x bigger than the number 2, that series doesn't converge. It doesn't give you a number. That doesn't mean that the logarithm function is not defined. It is defined, and it works well, and it has a number, but you cannot reach that number by successive iterations of improving this thing. Does that make sense?
And I think also like I don't know, remember too much, but when we first learned about spin, you try to model it before by a particle spinning, but like if you like, there's no way you can look at it in a classical picture and say, oh, that's come from its effect. Like spin is actually like an intrinsic effect, and so that's where kind of like you cannot have perturbation and then explain these things. You have to have new insights or new framework to explain.
Yeah, very good question. Any more questions or comments? Well, it's not that this is the last time that you can talk with me. We both live in front of my office. With that, I thank you both. I thank everybody for watching, and for people watching the video, I will see you in the next video on quantum mechanics. I don't remember what I talked about the second class, but it will be soon. Thank you, friends.